what worked just about 15 minutes ago. There, do you see the title slide?
Yeah, yes, I do. It's perfect.
Great. Okay, cool. Yeah, so this completely takes over my screen. So unfortunately, I won't be able to see your faces as I go through this, but you'll enjoy it. And then we'll come back for the questions. Okay, so let's talk about this nonlinear model of innovation. And I just want to start with a simple question. What is the relationship between science and invention? Now, on the face of it, you might think this is a pretty easy question. Obviously, science is the foundation of technology. By the way, I will use the words invention and technology more or less interchangeably in this talk. So yeah, duh, of course, science is the basis of technology, right? I mean, it's, you know, everything in our modern world seems to depend on science. Can't imagine having a smartphone without the science of electromagnetism or the physics of semiconductors. Can't imagine antibiotics without understanding microbiology. And indeed, if we look historically, the scientific revolution came a couple hundred years before the Industrial Revolution. Here's a couple of key figures from those to just sort of represent some of the early or starting points. Bacon lived from the 16th to the 17th century. Watt was mostly a 18th century, lived into the 19th century. In fact, Bacon himself told us in his Novum Organum, or New Method, published in 1620, that knowledge and human power are synonymous. For where the cause is not known, the effect cannot be produced. Nature, to be commanded, must be obeyed. This is where we get the aphorism, knowledge is power. It's condensed from that passage. So, all right, Bacon has told us where the cause is not known, the effect cannot be produced. Obviously, we need science to create technology. Except for that pesky problem of the historical record of invention. It turns out that there are plenty of inventions that came a good ways before the science that explains them. Sometimes decades before, or even they're in different centuries. So the steam engine, very famously, was invented in the 1700s. The science of thermodynamics didn't come along until the early 1800s. There are plenty of other examples. The first vaccine for smallpox and the early efforts at sanitation reform, especially water treatment, came long before, decades before the germ theory. Some of the earliest polymer materials, like cellulose, which is an early sort of protoplastic made from plant material, or vulcanized rubber, came long before polymer chemistry. They came in the 1800s. Polymer chemistry started to really get figured out in the early 1900s. In fact, sometimes the relevant science here was not just came after the invention, but was directly motivated by the existence of the invention and trying to understand how it works and to optimize it. So the first example here is a key case. It's been said that thermodynamics owes more to the steam engine than the steam engine owes to thermodynamics. So on this basis, some people have developed a kind of a tinkerer model of progress or of innovation. Nassim Taleb wrote in the Wall Street Journal, tinkering by trial and error has traditionally played a larger role than, quote unquote, directed science in Western invention and innovation. Britain's historical rise in the Industrial Revolution came from tinkerers, emphasis added here, who gave us innovations like iron making, steam engine, and textile manufacturing. The great names of the golden years of English science were hobbyists, not academics. And he names Darwin, Cavendish, etc. Okay, you get the idea. What I want to do in this talk is try to resolve this paradox. And I'm going to do it by clarifying the nature of the relationship between science and technology, which I think is subtle. And I'll conclude at the end by just hinting at, sort of indicating some directions that this might take us in when we think about how we manage R&D, research and development. So I think the paradox comes from sort of taking a little too seriously or naively an oversimplified linear model, quote unquote, linear model of innovation. Now, I'll say up front that the linear model is and sort of always has been a straw man. It's not like a worked out academic theory that somebody proposed and defended. It's always kind of been a foil, a naive or oversimplified view that people contrast their theories with. Although I think it has some purchase in the popular, maybe in popular consciousness and possibly in science policy. You often hear it attributed to Vannevar Bush's 1945 report, Science, the Endless Frontier, although it's been around since before that. And since there's no one sort of formal model of it, people divide it into multiple different, sometimes you'll see it in 3, 4, 5 phases, whatever, they're called different things, pure research versus applied or basic research, It doesn't really matter. I like to think of it in a very simplified view: science, invention, and distribution. And the kind of naive take on this is that there's a flow, there's like a sequence. First, we figure out some science, then we apply that to invention, and then once we've invented something, we can distribute it through a business or some other effort. Now, there is an important element of truth in this, and we'll spend a good amount of time looking at what that is. But a naive interpretation is, a little detached from reality. So the naive interpretation, I'm going to just caricature this. I call it the clean handoff model. And it's this idea that science is purely upstream of technology, that the relationship is sort of one way. To elaborate, it's the idea that science is motivated by pure curiosity. We're not thinking about applications. We just just the free play of the intellect. We just we just want to understand the world. That's all we're thinking about, pure understanding, You see a little bit of this in Vannevar Bush's report, Science: The Endless Frontier. He talks about this. And that science always precedes invention. The science always comes first, and then the invention comes along. We've already seen examples that disprove that. That science kind of comes up with these clean, elegant natural laws, just very crisply formulated, and then are thrown over the transom to engineering, Okay, now you please, engineers, go figure out something useful to do with this, right? And then that engineering itself or invention is kind of a straightforward deductive application of science. Okay, I've caricatured this as hard as I can to make a point. Every one of these bullets is wrong. Okay, so I think there is, like I said, an element of truth in the model. Science is the epistemic base for invention. That term epistemic base, by the way, comes from the economic historian Joel Mokyr. I particularly recommend his book, The Gifts of Athena, on this topic in general. And so we will spend about half our time looking at how is this true? How is it that science provides the epistemic base for invention, especially given this sort of, these tinkering examples that we've seen. But here's where it's wrong. Technology gets ahead of science, again, as in the examples that we've seen. And as we'll see, technology feeds back into science. So there are feedback loops. The relationship is not one way. It is reciprocal. I am not, by the way, talking about the obvious fact that science requires the invention of instruments, such as the microscope, the particle accelerator, etc. Those are ways in which science depends on technology. But that's even a little too obvious. I'm talking about something more subtle. Okay, this is the summary of kind of what I'm talking about. We'll spend most of the time elaborating on these points. To understand this, let's go into a case study. Let's talk about that quintessential invention of the Industrial Revolution, the steam engine, right? Pretty much defines the era. Now, again, it's been said that thermodynamics was not needed to invent the steam engine, and this is quite true. But what was needed was another science or another field of science, specifically the scientific concepts of air pressure and the properties of the vacuum. So very briefly, the way the early steam engines work. So all steam engines have a piston, and steam is pushed into the piston. The early steam engines, so the very first working steam engine was invented by Thomas Newcomen in 1712. This is, I believe, a replica or model of it from the British Science Museum. And the way it worked was you had a big piston, and you'd fill it up with steam, and then you would spray cold water into the piston, which would condense the steam rapidly, form a vacuum, and then the outside air pressure would actually push the piston down against the vacuum. Later versions of the steam engine used high-pressure steam, and the steam itself would actually push the piston. And in fact, there were versions that pushed it in both directions, so you'd get high-pressure steam on one side, then the other, and so forth. But that's not how the earliest steam engines worked. They worked by creating a vacuum. So you needed to create this, you needed some idea that vacuums existed and that air pressure existed and could push against the vacuum and actually push the piston. And that science was worked out, in fact, in the 1600s. So it was, I believe, Evangelista Torricelli, the Italian scientist, who first demonstrated in the 1640s that the air has weight. In the 1650s, a famous demonstration was done called the Magdeburg hemispheres. They are illustrated here at the top. Two hemispheres of metal, I believe they were made of copper, that could be pressed together, and then the air pumped out of them. So they had air pumps at this time, and they could create vacuums in sealed chambers with an air pump. And then, so these two chambers, these two halves were placed together to form a sealed chamber. The air pumped out of them, and then let's zoom in on the middle here so you can see what's going on. They actually tied a team of horses to each half and strained, at the hemispheres to try to pull them apart with all of the traction of these horses. So this demonstration was performed, perhaps among other times, in 1654. According to Wikipedia, 30 horses in two teams of 15 could not separate the hemispheres until the valve was opened to equalize the air pressure. And then, of course, they just fall apart. So this demonstration was performed in the mid-1600s, and this, so this kind of basic scientific principle was known that early. In fact, it is believed that Thomas Newcomen corresponded with scientists through the Republic of Letters, wrote letters to each other, including Robert Hooke. And there is a report, although this is unconfirmed, that Newcomen discussed his steam engine that he was trying to invent with Hooke, and that Hooke specifically advised Newcomen to operate the steam engine entirely by means of a vacuum. I believe that someone else refers to this letter and says that this exchange happened, but we've never actually found the letter, so chalk this up as unconfirmed. But there are some other connections between science and steam that are known and established. So decades later, James Watt is looking into the steam engine, and he makes a famous contribution. So Watt did not invent the steam engine, but he invented a new and much more efficient version of the steam engine. In brief, what was going on was, I mentioned that in Newcomen's engine, the steam was condensed in the piston. The problem with this is you have to cool down the piston to condense the steam and then heat it up again. So the entire piston, which is very large, is getting cooled down and heated up every cycle. Watt came up with an idea that you could cycle the steam through two chambers, a cold chamber where steam got condensed, and then a hot chamber where it was expanded. And you didn't have to then keep cooling and heating the same thing. So it was a lot more efficient with fuel. This is known as the separate condenser, and this was Watt's, like major contribution. And in order to get to this, Watt was doing a bunch of experiments with the steam engine and measuring the amount of heat that went into different things and what was going on. And he noticed that a lot of heat seemed to go into turning water into steam. And he didn't know what would explain this. And he goes to his friend, Dr. Joseph Black, who's at the same university. I think it was the University of Glasgow. I'm blanking on which university it was. And Joseph Black is what we would now call a physical chemist, and says, "Aha, yes, you have rediscovered my theory of latent heat," and explains to Watt sort of what's going on. And this understanding was important to Watt's separate condenser and more efficient steam engine. And it was after Watt that the steam engine really got going and people started applying it to a lot more things. Decades later, Robert Trevithick is doing experiments with high-pressure steam engines. Trevithick wants to make a steam engine with a better power to weight ratio such that it can actually be used on a vehicle. Trevithick invents, in the early 1800s, he builds the first working prototype, really, of a locomotive. And in doing this, he was wondering whether he could dispense with the complexity of the separate condenser and this whole cycle of condensation of the steam by, instead of recycling the steam, just venting it in the atmosphere when you were done with it. And he wasn't sure how this was going to affect the efficiency of his engine. So he goes to his mathematician friend, Davies Giddy, who understands the physics of gases as it's understood at the time. And he asks Giddy, what's going to happen if I just vent to the atmosphere? And Giddy assures him, oh yeah, you won't lose a whole lot of, if you had something if you had an engine at 10 or 15 atmospheres and then you vent the steam out, you're just going to lose 1 atmosphere of pressure. It's not going to be a huge deal. And this allowed Trevithick to invent high pressure engines with a simplified design. So all of the major innovators in steam engines, it seems, had some contact with scientists or mathematicians who understood the relevant theory and helped them in their work. Now, yes, of course, thermodynamics came along later. It's traditionally held to begin in the 1820s with Sadi Carnot. Thermodynamics came along to understand the workings of these heat engines and their cycles, and ultimately to help optimize them. But that sort of came along later for efficiency and power and that kind of optimization. So just from this case study, we start to see some general patterns. Science comes along and identifies some key concept, a key phenomenon that can be exploited by inventors. Inventors come up with a machine that does performs some useful function, and maybe whose operating characteristics are not completely described by the science we have so far. And then more science comes along to explain the workings of the machine and let us optimize. And note, by the way, that so this pattern, it's not exactly always like this every single time, but this general pattern is common. Note, by the way, that the invention of the heat engines led to the field of thermodynamics in two ways. One, it gave science a new phenomenon to study, these engines. But also, it gave motivation to explore this particular corner of the universe. Right? These engines are useful, and optimizing them would be economically useful. But to come back to this concept of the epistemic base, you need that epistemic base. You need to know about the vacuum and about air pressure. If not, what do you get? Well, you get things like Hero's engine, also known as the Aeola pile. This dates from antiquity, like the 1st century or something. I don't remember exactly when. It is sometimes called an ancient steam engine. This, in my opinion, is inaccurate and misleading terminology. It is not a steam engine. For one, it's a turbine. It doesn't have a piston, right? It doesn't drive reciprocal motion in a piston motion. It's really just it's a boiler, and it's got a couple of little arms that stick in opposite directions, and steam goes out the arms, and that makes it spin. But it's basically a toy. It's not useful for doing practical work because it does not generate a lot of torque. And it was going to be a long time before we had steam turbines that actually generated useful work. So, so this is the difference between the concept of I'm going to make steam engine versus I understand. I have vacuum. I understand that vacuums can be created, and I understand air pressure and so forth. A dramatic example of the need for an epistemic base, I think, is the case of vaccines. The very first vaccine was created in the 1700s by Edward Jenner, who created a vaccine for smallpox. I can talk about this at length in the question period if you want, but very briefly, before vaccines were invented, there was a prior technique called inoculation, where you literally actually gave people a mild case of smallpox in order for immunity. Jenner was the one who figured out that, indeed, we could do this with an even milder and safer disease, cowpox. So we could substitute cowpox for smallpox, inoculate people with cowpox instead. He called this vaccination. And by giving them a mild case of cowpox, it was even safer, and it would still confer some degree of immunity, or immunity for some period of time against smallpox. Now, this was great. But nobody came up with any vaccines for any other diseases for almost 100 years. My interpretation is essentially we needed the germ theory. And we'll see that, in fact, one of the pioneers of the germ theory was the one who created the first engineered laboratory-created vaccines, the first vaccines after Jenner, almost 90 years later. But without that epistemic base, so how far did tinkering get us? Well, it got us one vaccine. We managed to stumble onto this without having a general theory of what causes disease, or sort of knowing that science. But that was as far as we could take it. No other vaccines were created until we had a broader theory and scientific methods for experimenting with disease, which was maybe even more important. In fact, not only can you make some progress with no theory, it turns out, but you can also make some progress on a wrong theory. And a great example of this is the efforts of the early sanitation reformers. So Max von Pettenkofer and Florence Nightingale were both key figures in the mid-1800s sanitation reform movement. Pettenkofer advocated for cleaner water sources, like taking your water from clean sources upstream, making sure to dump the sewage downstream, maybe even filtering the water through sort of earlier primitive kind of filtration mechanisms. And he got cities in, I'm blanking on what it was, Germany or Austria or whatever it was to clean up their water. Florence Nightingale did a lot of work, of course, in hospitals and medical settings, improving sanitation there. Neither of them believed in the germ theory. In fact, not only that, they sort of actively opposed it or ridiculed it. Florence Nightingale wrote some scathing things about ridiculing germ theory. Pettenkofer had this famous debate or disagreement with Robert Koch. So Koch is one of the two key figures in establishing the germ theory. And Koch was saying that bacteria were responsible for cholera. And Pettenkofer decided to disprove this. He was so convinced that just the bacteria alone were not the cause of cholera that he actually drank a bunch of cholera bacteria in a demonstration to prove that, this theory is ridiculous. Somehow he survived. We don't totally know how. Seems like maybe he had a mild case of cholera, or maybe he'd had some sort of pre-existing immunity. But that's how convinced he was. So you might wonder, well, how did these people make any progress at all if they had the wrong theory? Well, they had a sort of right theory. They had a theory with some truth or plausibility to it. They also had empirical correlations. So ever since the 1700s, people have been trying to collect data and just form empirical correlations between certain conditions of the environment and disease. And they had noticed that certain kinds of filthy conditions, were related to disease, and that was correct. Also, by the way, evolution endowed us with a sense of smell and a sense of disgust, which to a first approximation are not bad, ways to kind of avoid disease. And so, some of these early reformers were driven as much by aesthetic sense as by, health considerations. They wanted, and in fact, the early efforts to clean up the water were driven by taste, smell, color, things that you can directly perceive, and that your natural sense of sort of cleanliness or aesthetics is going to guide you in basically in the right direction. But it can only guide you so far. And what happened was eventually, so we were able to clean up the water somewhat, but eventually when we got the germ theory and that had been really established and proven, and not only did we have the science or the concept behind the germ theory, but we also had methods. Robert Koch gave us methods to test the water and count the bacteria and actually, quantify something about the concentration of harmful bacteria in the water. And with that, we could start to actually do another round. So after the mid-1800s, in the late 1800s in Europe, and then early 20th century in America, we started to really clean up the water supply. This is a cartoon from 1919 representing, I forget what city exactly, I believe some American city that this is sort of representing progress in. So in 1890, you can see typhoid, which is a waterborne disease, reigned. Typhoid here is represented as sort of a skeleton monster with a cape and a top hat, smoking a cigar or something like that. In the second panel, the water filtration plant comes along to start beating him up. And in 1906, the death rate was reduced. And then in the third panel, liquid chloride has been added to the water supply, and that's a chemical that is going to kill the bacteria in 1918. So this happened at different times in different cities. The association between the filtration and chlorination and the disease rates are quite dramatic. So again, we see, based on no theory, but on some empirical correlations or even on a wrong theory, some progress was able to be made. That progress plateaued at a certain level, and then a better scientific understanding came along and allowed us to go even further and to optimize, the processes that we were doing. Okay, so science can provide concepts that point inventors in a promising direction, give them phenomena to exploit. It can also help optimize and expand the workings of existing inventions or systems. It can also guide the tinkering process itself. Just a couple of quick examples here. Edison and his lab famously tested thousands of materials to create a practical, long-lived light bulb. This is often portrayed as sort of a haphazard search. But Edison actually understood more of the science behind this stuff than he is typically given credit for. And unlike other many other inventors of his day, Edison realized that to make an efficient light bulb system, and power generation system, you actually wanted the light bulb filament to be high resistance, not low resistance. And that was going to optimize the power requirements of the whole system. And so, that, among other things, was guiding sort of the search. That's why he was testing things like cotton filaments and bamboo and, that sort of stuff. Another example is the way we screen drugs. So drugs are often found by just screening a whole bunch of, known compounds and just testing a whole bunch of things. But, sometimes the way we even find those compounds is that we start from known compounds, and maybe ones that have some sort of activity, that we think is related to what we want to find. So, in fact, the entire field of antibiotics got started in part because there was this German scientist, Paul Ehrlich, not to be confused with the population bomb guy, by the way. That was a different guy, an American, much later on. But the German, Paul Ehrlich, sort of the father of antibiotics, in a sense, he had developed the technique of histology where you could stain tissues to sort of see them under the microscope. And he found that certain chemicals would stain bacteria and not stain the surrounding tissue. And this gave him a hint that we might be able to find what he called the magic bullet, which is something that would kill the bacteria and not damage the surrounding tissue. That's what you need for antibiotics. We already had ways to kill bacteria, like with bleach and acid and heat. Those things don't work in the body because, of course, the trick is to kill the germ without killing the host. And so we needed a special chemical that was going to selectively bind to the bacteria and kill it. And so Ehrlich noticed that we had these things that selectively stained the tissue. He thought, aha, what if a similar compound selectively kills the bacteria? He had this theory, which is correct, that these molecules were fitting into each other in a very precise way, like a key in a lock. And so some of the early, drug experiments were based on modifying dyes. And that's how I believe that's how they found some of the early antibiotics, like in the 1930s. So why do we need an epistemic base? Well, a key reason is that the search space is just absolutely enormous. Driving this home, Richard Nelson wrote a classic paper in the 1950s when he was at the Rand Corporation called The Simple Economics of Basic Scientific Research, and he gave these compelling examples. One was, what if you got some scientists at the turn of the last century, to come up with a better way to examine the inner organs of the body? They would never have come up with X-ray analysis, right, if they hadn't already identified that, X-rays existed and what they could do. Similarly, if a bunch of people in the mid-19th century had tried to come up with a better method of long-range communication, just starting from that goal without the science, they would never have figured out Maxwell's equations or developed radio. The other reason, so the search space is enormous, but the other thing is that the devil is in the details. Tiny, seemingly insignificant changes can make the difference between success and failure. And so not only is the search space huge, but you can be right next to the right thing and miss it completely. What if you tuned into just the wrong frequency? Or what if, you boiled the water you needed to boil the water for just like 1 minute longer, and you didn't know that. You can fail completely. So you don't always know when you're close. And so this is what we need, theory to guide us for. So science, to wrap up this part, forms the epistemic base for invention in at least 3 different ways. It comes in before, during, and after the invention process. Before, it identifies phenomena that can be exploited, such as the vacuum, or germs, or semiconductors. During the process, it can guide and focus the search. And then after the invention process, it can help us optimize the inventions that we come up with for power or efficiency, etc. And it can help extend them to new domains, as we extended the concept of the vaccine to other diseases. Okay. So that ends sort of the first half. That is sort of what was right about the linear model, the grain of, or the element of truth in it. Now let's look at, where the linear model is wrong. As we've seen, engineering gets ahead of science. Engineering can come up with inventions that were not predicted by science or that aren't explained by it. Sometimes we don't even know how the invention works, why it works at all. Sometimes we sort of know the basic principle, but we don't know why it has the operating characteristics it has, etc. And I'm going to suggest that this is not just a historical phenomenon. This isn't just a thing that happened in maybe in the early days of the Industrial Revolution, but actually engineering will always get ahead of science. Now, one reason for this is economic. That's where the opportunities are. You know, if you imagine that we waited until science had fully described an area before we went in and started making inventions, well, first off, why wait to create economic value? You never want to wait if you don't have to. Also, by that point, the competition is going to be intense, right? Everybody's going to be trying to do something once an area is understood really thoroughly. So if there are valuable things to do that are just barely possible, but difficult, and some small set of people who have training and can understand how to tinker in a certain area can go maybe do the hard, valuable thing, they're going to go do it. And I think we see this in many cases. We see it in the transistor, which we'll talk about in a sec. See it in the light bulb. You know, you see it in vaccines, etc. But I'm going to go a little further. I think it's not just an economic reason that engineering gets ahead of science. I think there's a deeper reason. I suspect that tinkering has to happen outside the bounds of science. To explain why, let me do another case study. This time, the transistor. So this is a picture of Bardeen, Brattain, and Shockley at Bell Labs, who shared the Nobel Prize for the invention of the transistor. And the way that it happened is pretty remarkable. So Bell Labs creates a semiconductor research group in late 30s or maybe around 1940. The basics of semiconductor physics had sort of been worked out at that time. That happened in the 1920s or 30s or so. And it was clear that to a number of people who were close to this that there was potential here. There was a fertile field. They were on the verge of something. Ooh, we could do something great with this semiconductor stuff. We could invent some interesting electronic components. They didn't know exactly what they were going to invent. They weren't sure that they could make a transistor, and that wasn't the only thing they were trying to make. But a transistor was one of a number of things they thought could be possible. Shockley, in particular, was optimistic about being able to create a solid state. They didn't call it the transistor yet at that point. They called it the solid state amplifier, was the theoretical thing that they were trying to create. And there were other solid state things they might thought they would be able to create, but they were experimenting. They were trying different things. And one of the things they tried to do was, so they tried various ways to create a solid state amplifier. And what was remarkable to me about this process was how they actually shuttled back and forth between science and invention. They kept going back to the drawing board and then back to the workbench multiple times. So they started with the theory of semiconductors, right? The basic theory that had been worked out by physics. Again, you need that epistemic base. You need those concepts. If it weren't for the theory of, for the concept of semiconductors, Bell Labs would never have created a semiconductor research group. So then on the basis of the theory that was known, they tried a couple of different ways to do it. One of the ways that they tried was something called the field effect amplifier. That was a design they came up with. It didn't work. That design failed. It did not produce a very large amplifying effect. It was orders of magnitude smaller than the theory predicted. Sometimes I think it was in the wrong direction. So they didn't know why. So they went back to the drawing board. They went back to theory. And they said, okay, let's try to understand why this is not giving us the same effect that we predict, that the theory would predict. And one of them, I think it might have been Bardeen, might have been Brattain, I'm forgetting which, said, look, what if something is going on at the surface of the material? What if the electrons are bunching up in a way or sort of like behaving in a way at the surface of the material that's different from the way they behave inside the material? What if we need to account for this? The theory hadn't accounted for this. So he came up with this theory of surface states. And then based on that theory, they went back to the workbench and said, okay, if this is the way it works, let's try to do some more experiments and create a transistor. And they were doing a number of experiments, and one of them that they set up, because of this, that they didn't even expect to create an amplifying effect, actually created an amplifying effect. And so here, now, whoa, they'd gotten an amplifier when they weren't even, expecting one. And so this was called the point contact transistor. And so then, to explain why they were getting, before they went to theory to explain why a thing failed, now they wanted to go back to theory to explain why something unexpectedly succeeded. And they came back to a concept that had already existed, but that had not been emphasized, which is the concept of minority carriers. So if you know a little bit about silicon and semiconductors, you know that there's two types of silicon. There's N-type and P-type, which we create through doping the silicon, meaning creating very tiny impurities of elements like boron and phosphorus. N-type silicon has an excess of electrons, and so negative charge flows through it very easily. P-type is positive, and it has a deficiency of electrons, and positive charge flows through it more easily. But it's possible for positive charge to flow through N-type and for negative charge to flow through P-type. And this is known as minority carriers, the positive charges or negative charges flowing through the area where they're not the majority. Now, it was known that this could happen, but it wasn't known how important this effect was. And so the researchers at Bell Labs sort of resurrected the theory or gave new emphasis to the theory of minority carriers and realized that it was affecting things more than they thought it would. And on this basis, Shockley actually went and designed the junction transistor, a different design for the transistor that depended on these minority carriers, and that became the design that they actually ran with and scaled up. So they were really shuttling back and forth here between science and invention. And I have to look, just looking at this, I have to wonder, if they hadn't been doing this invention, if they hadn't been trying to make a transistor or other solid-state electronic components, how long would it have taken pure physics to get around to investigating surface states? Would physics ever have realized the importance of minority carriers? Maybe. Maybe not. Maybe it would have taken a long time. Maybe technology had to get out in front here and point the way. Kind of get out ahead and then pull science along behind it. And so I'm going to go out on a bit of a limb here and suggest that maybe technology actually can't wait for science. Not just that it doesn't want to wait, not just that it shouldn't wait, not just that it can't afford to wait, not just an economic reason for to be experimenting at the boundaries of what is known, but maybe we actually need a separate and overlapping set of incentives. Maybe we need to point science into different corners than it would otherwise go if it weren't for invention getting out ahead and tugging at it. After all, I mean, I think it's certainly clear that we do need the incentives of pure curiosity. If we only had the incentives of technology and practical applications, if we were like very myopically utilitarian and like we're only going to focus on things where we can see direct applications, well, then we'd be nowhere, because much of science has come from just exploring, just trying to understand the world, that pure curiosity. There's nothing wrong with that pure curiosity motive. It exists. It's important. It has driven us to explore and understand the world. And then that understanding that comes from pure curiosity gives us applications that are amazing and transform things. But I think, but it's one lens on the world, right? That curiosity, and it directs science into a certain set of corners of the universe to explore, and technology, practical applications, it's just a different overlapping set of incentives that points you maybe into different corners that you would never have explored. So I think that maybe experimentation towards an invention is actually necessary, not just valuable, but needed to uncover the right phenomena and to point science to things that it wouldn't otherwise be looking at. To wrap up this part, where the naive linear model is wrong is that science is not upstream of technology in a couple of ways. Technology gets ahead of science. I'm arguing here that in fact it must get ahead of science, and then technology feeds back into science. So as we've seen, technological experimentation and invention can give science new phenomena to study and the motivation to study them. All right. So what? What's the upshot of all this? What can we conclude? Well, there's a simple sort of epistemic thing, which is just giving theory its due. And part of why I wanted to give this talk was to kind of rescue theory from the pure tinkerer model and to point out how important, essential, indispensable theory actually is. But I think if we take this idea seriously and we think about what are the practical implications, I think it can point us in certain directions to think about how we manage research. In the case study we just saw, the transistor at Bell Labs, we've seen that science and engineering can be tightly integrated in a single project. Under one roof, in one lab, you had people going back and forth between the chalkboard and the workbench, so to speak. Before we conclude, let me look at one last case study. Ha, you thought I was done with case studies, didn't you? You thought I was wrapping up. Okay, you're going to get one more case study, a real hero of mine in the history of science, and somebody whose career absolutely exemplifies this integration between understanding and practical applications, and that is Louis Pasteur. Pasteur had a really amazing career. He was one of the founders of microbiology. Along with Robert Koch, he established and demonstrated the germ theory of disease. And he also created the first laboratory-created vaccines, the first vaccines since Edward Jenner. Early in Pasteur's career, when he was still more of a chemist than a microbiologist, because microbiology barely existed at that point, Pasteur was asked to help the wine, beer, and vinegar makers of France. It's something that seems almost comically utilitarian when you look back at, what an amazing scientist this guy was. But Pasteur didn't think of this work as beneath him. And he went out and he helped these folks with their fermentation processes. They were having trouble. They weren't getting consistent results. Sometimes the wine or the vinegar or whatever would turn out bad. They didn't know why. So Pasteur goes and he's exploring what is going on with this fermentation, what causes the different outcomes, and he realizes something that had been hypothesized or had been put forth by others, but that had not been conclusively demonstrated and had not been accepted generally, which is that microbes in the wine, beer, etc., were actually driving the fermentation process. The scientific establishment at the time did not want to believe this. It smacked of vitalism. But Pasteur, through diligent and careful experiments, showed that the microbes, that the yeast and bacteria and so forth that we found in these substances were not just incidental, nor were they simply feeding off of the fermentation, but they were actually driving it. And in fact, through this, he discovered that part of what was going on was that fermentation was driven by anaerobic metabolism in these microbes. That when they were cut off from oxygen, when they could not use oxygen, they switched to metabolizing sugars and turning it into alcohol and carbon dioxide. So I just think this is amazing, right? Pasteur goes into this very utilitarian, just kind of like process optimization within industries, not even industries, but like crafts, that had been around for thousands of years. And along the way in, just trying to make wine and beer better, he discovers these fundamental principles of microbiology. So it's interesting to me how, he was able to sort of pivot from a very utilitarian practical concern to a very scientific theoretical concern. But he also pivoted in the other direction as well, perhaps even more dramatically. Later in his career in the 1880s, when he was doing experiments on farm animals to try to figure out what diseases that they would get. This picture is of a rabbit, but it was actually, he was doing experiments with chickens and something called chicken cholera. Through a botched experiment, his lab accidentally discovered how to make a vaccine. And he discovered the mechanism of what is known as live attenuated vaccines. And he immediately realized the importance of this. He realized that he had been able to do, by accident through a botched experiment, what no one had done since Jenner. For generations, for almost 90 years, no one had been able to come up with a vaccine for another disease beyond smallpox, and here he had accidentally done it in the lab. And he immediately pivoted his attention to that, started creating vaccines for chicken cholera, for anthrax, which affected sheep, for a disease called swine erysipelas, and then he created the first engineered vaccines in humans, beginning with rabies. And when word got out, by the way, that he had even a potential rabies vaccine, patients started flocking to his office, people who'd been bitten by rabid animals and knew that they were at risk of developing rabies, which is a very slow developing disease, by the way. It takes like a month to really show symptoms and kill you. And so it's one of the few diseases, by the way, where you can actually benefit by getting the vaccine after you've been exposed. And so people who've been bitten by, rabid dogs and animals started coming in to him and say, I heard you have a vaccine. Please save my son, save my child, save my life. And so Pasteur was very reluctant at first, especially when he'd never tested, or hadn't sufficiently tested the vaccine. He gave the rabies vaccine to a child who doctors assured him had been bitten so much that he was a goner anyway, saved the child's life. More people come, and Pasteur realizes that he's got to set up a clinic. he's got to scale this up. And so I tell this story because Pasteur is maybe the only example I know of where somebody actually spanned all three of the phases of the linear model that I set out in the beginning. He was a scientist. He invented techniques like vaccination, and then when it came time, he scaled it up to distribute it to more people. So he's a real hero of mine. And an amazing career that integrated discovery and invention. I think these examples demonstrate to us that science and technology should be tightly integrated in our programs and institutions for research. We should think about this in training. Do we train people for both roles? In career paths, if somebody wants to pursue a role like what Pasteur did, or those folks in Bell Labs where they combine discovery and invention, is there a way for them to do that? Not sure there is a great way right now. In our projects and programs, the institutions that house them and the funding, mechanisms that we have, we need to make sure there are dollars that are not just earmarked for pure basic research and not only earmarked for development or engineering, but that are, that we can spend on both. Now, I've only begun to really investigate how this stuff used to be managed and how it is set up today. But it seems to me that science and invention are not as integrated in our world as they used to be. Part of this is owing to the increase in specialization, of course. Part of it is owing to the decline of corporate research labs. There's really nothing quite like Bell Labs anymore. And maybe there are other factors as well. I don't know what they all are. But I think this is, I'm just going to say this is, I don't have a big policy prescription here or anything, but I'm just going to say I think this is a direction that we should look at when we're trying to figure out, causes of stagnation and ways to accelerate progress. Because if we want more breakthroughs like vaccines and transistors, I think we're going to need more folks like Pasteur, Bardeen, Brattain, and Shockley, who combined science and invention. Thank you all. Please subscribe to my blog, rootsofprogress.org. Follow me on Twitter. I'm Jason Crawford. And I guess now we'll go to questions.
Good. Well, thank you, Jason. And now I'll read off some of the questions we've had so far, but everybody should feel welcome to ask more questions in the text chat. So Mr. R asks, how much do you buy Hanson's model that innovations are lumpy and that they're mostly incremental?
I haven't read what Hanson wrote on that. Innovations are lumpy. Yeah, that sounds accurate. Mostly incremental. Yes, that also sounds accurate. I would recommend, there was a good blog post by angel investor and professor Jerry Newman. His blog is actwheel.net, I think. And he wrote a fascinating blog post called One Process, where he asked the question of, is it the case that there are two processes, like I think it was Thomas Kuhn, who talked about you kind of got like the incremental science, and then you have the paradigm shifting revolutionary science. And you can see some things like this in engineering as well, where we have these revolutionary advances like the transistor or the integrated circuit. And then we have also a lot of just like incremental improvements in things. And so Newman asked the question, are there two distinct processes that generate these two types of things, the revolutionary versus the incremental? Or is there one process that generates innovations that have a power law distribution? And we think there's two types because we see a lot of really big ones and we see a lot of tiny ones, and we don't see like a whole spectrum of things like we sort of expect because we're just not that attuned to power law distributions. And he has sort of a good argument that the latter is the case. So yeah, there are huge changes, there are small changes. We shouldn't over focus on the huge changes and neglect the role of a lot of incremental innovation. A lot of progress just comes from compounding, 1% improvements like every year, 2 or 3%. Yeah, absolutely.
Kevin Uzomeshin asks, how do you think AI will affect various models of innovation? Or more precisely, what will be the impact of AI on both the pace scale of innovation and on society itself?
I rolled my magic 8-ball and it says future is cloudy, try again later. I don't know. I don't have a great, and I'm not sure anybody can really know. And if there are people who can really know, it's probably people who've spent a lot more time thinking about AI than I have. I don't know. I think it could be big. It's one of these things we're on the verge of, and it's hard even to know how far away some of the big breakthroughs are, let alone really how it's going to transform things. Let me say one thing on this. And this is sort of maybe, I think this is a contrarian position, especially in rationalist circles. It is not at all, I think it is often assumed that the type of intelligence that machines have or that we can create in them is essentially of the same kind as the type that we possess through our biological brains and consciousness. And that there's just sort of like a sliding scale, and the computers are getting smarter and smarter, and eventually they'll get better than us. It is not at all clear to me that that is the case. I think it is quite possible that machines have a distinct type of intelligence, just like, a car doesn't travel the same way that a horse does, and a washing machine doesn't get clothes cleaned the same way that a human does at a washing clothes by hand. I think machines don't think the same way we do. And so I don't think you can simply extrapolate from machines where they are now, or, the scale from like mice to monkeys to humans, and then something beyond that. I'm not at all convinced that, that you can just put things on that scale. Maybe you can, but it's not, I don't think it's obvious. I don't think you can start with that assumption. So that it makes it even harder to sort of know where things are going.
Okay. Eliezer Yudkowsky has said that there must be a solid theoretical foundation. First, if the world's first AGI is to be aligned, to be friendly. He believes, on the other hand, that unsafe AGI can be created with tinkering, trial and error. Any thoughts on this?
That's an interesting idea. Makes sense on the face of it. I don't know. But, certainly, if you're tinkering with no theory, you have much less of an idea of what you're going to get. So if you're concerned about safety, I think having more theory, makes sense. Seems like a good place to invest.
Okay. Mr. R asks, what caused Germany to overtake Britain as Europe's leading center of industry past the 1870s?
I'm not an expert in this, but the big thing that Germany was good at was chemistry. A significant, so there's a couple of things. So they had a couple of the top chemistry companies, Bayer, BASF, Hext. And they also had sort of tight collaboration with university. So Germany in the 19th century is the birthplace of the modern research university. They kind of pioneered the model. Universities had been around since the Middle Ages, or maybe longer, but they were, they started off as much more kind of, they trained the clergy and people who were going to go into law and politics and doctors and stuff. But of course, they didn't really have science at that point in like the 11th century when Oxford or whatever is getting founded. And so the notion of the university as a place of research primarily, not even primarily a place of teaching, but where both the student and the teacher were in the service of research, is really kind of a 19th century German notion. Look up Humboldt and the University of Berlin for a reference there. And so the German universities became these sort of research places, and they got pretty good at chemistry. and the chemistry companies had these close associations, and so they sort of took off. By the way, if you were an American in the mid to late 1800s and you wanted to go get a technical education, especially in chemistry, you had to leave America. America didn't have any good universities. You had to go to Germany, or at least somewhere in Europe, but usually Germany, get your education there, and then come back. Just like immigrants today come to American top universities and then go back to their home country. That's what Americans were doing, going to Germany for their chemical education. So I think that was a key part of it. And so then Germany pulled ahead in at least the chemistry industries. And I don't know what else, but that's a key part of the story.
Another question, and everybody, again, feel free to keep asking in the text chat. So João Medeiros asks, if technology has to get ahead of science, how do you understand the advent of general relativity and the previous existence of Riemannian geometry? What would be the technological counterpart?
I don't know enough about that, sorry. I don't understand relativity very well, and I don't understand Riemannian geometry at all. So I just don't think I can speak to that. Sorry.
Okay. Patrick asks, is there any nation or institution existing today that you think is innovating in the practice of encouraging innovation?
Not that I know of. And I haven't done a survey of it yet. But I feel like if there was something really significant going on, I would have heard about it by now. I think there are interesting models to look at, but I don't know of any nation that I would say, oh yeah, they're really surging ahead and doing some great experiments. I think some interesting things are happening in the US right now. DARPA is a model that a lot of people look to, and some folks in the UK want to copy. There's an interesting project going on right now. A guy named Adam Marblestone is working with something called the Day One Project to create something he calls focused research organizations, which are a little like DARPA type organizations and a little like startups, but focused on research and not purely DARPA has to be military research ever since the 70s. They're not allowed to do things they can't justify somehow on military grounds. So I think Adam and his focused research organizations is an interesting kind of project that just launched. Patrick Collison's and Tyler Cowan's Fast Grants experiment, I think, is an interesting experiment. There's some other things going on outside the U.S. and I can't remember off the top of my head which countries have experimented with this. But if you look up grant making via random lottery, is an interesting, very highly counterintuitive sort of experiment in funding research. And I can't remember which countries have experimented with it, but some countries outside the U.S. Maybe New Zealand. I don't remember. But if you just look up grant lotteries or something, you'll probably find some stuff on it. But these are fairly small, isolated experiments. I don't feel like there are major efforts going on anywhere.
Josh Sachs asks, how do you distinguish between experiments and tinkering? Isn't tinkering just another name for scientific experiments?
Yeah, and I don't really like the term tinkering for this very reason, especially when it is contrasted with science. I think that's a little silly. Science does lots of tinkering. There's lots of just trying things and experimenting and not really knowing where you're going or what you're doing with it, right? I think the real contrast here is between being guided by theory versus just sort of pure ad hoc bottom-up experimentation unguided by theory. And yes, there's a lot of very ad hoc trying things out in science, and there's a lot of very ad hoc trying things out in invention, and you could call both of those tinkering. Yeah, I don't know.
Patrick asks, besides intelligence, is there any surprising character trait or experience that is common among innovators?
Aside from intelligence, I haven't made a systematic study of this, so I can only give you my biases. I think that I mean, certainly a degree of persistence is necessary, because innovation requires a lot of messing around, a lot of failures and setbacks, and a degree of independent thinking is necessary, because nobody thinks that your stuff's going to work, right? Most people think you have no idea what you're doing. You're going to, you're barking up the wrong tree. Your stuff's never going to work, and you're a little ridiculous, and you have no idea what you're doing. And you have to be very independent-minded and persist despite all of that. And then, of course, when your stuff actually starts to work, that's when people switch from ignoring and ridiculing you to actively fighting you, and opposing you, and denouncing you, and so forth. So, you see different personality types among innovators. Pasteur was a little feisty. He actually kind of enjoyed the sport and the debate, and he enjoyed proving people wrong and having opponents. And he would be like, "Okay, I'm going to come in with so much data and so many carefully performed experiments. I'm just going to knock you over." He enjoyed that. Darwin, is different. Darwin is a little more quiet and shy, and he didn't love the public debate. Famously, Darwin had associates, friends, or colleagues who went out and did the debating for him. Was it Thomas Huxley was known as Darwin's bulldog, and he would go out and he'd be the one who'd get up there and debate like the priest or the preacher, whoever it was, who was there's a really famous debate between them. So there's not just one personality type, but I do think you have to be extremely independent-minded, have a lot of perseverance, and as Jeff Bezos says, you must be willing to be misunderstood for long periods of time.
Mr. R asks, why aren't there people innovating the practice of innovation? What would it take for us to do so?
So I think that's part of what the progress studies movement and community is about. So for those who aren't familiar with that term, last summer, Tyler Cowen, the economist from George Mason, and Patrick Collison, the co-founder of Stripe, co-authored an article in The Atlantic, which ran under the headline, "We Need a New Science of Progress." And they called for an academic discipline, or perhaps an interdisciplinary field, which they referred to as progress studies. And ever since then, there's been sort of a community of people who are interested in this idea of, let's actually focus on where does progress come from? What creates it? What are the conditions for it? And let's try to make more progress, Now, they pointed out in that article that they weren't proposing something that was brand new. This kind of thing has received some attention for quite a while. There are plenty of economists who, do the economics of innovation. Some names off the top of my head: Matt Clancy at Iowa State, Pierre Azoulay and Andrew Lowe, both of whom are at MIT Sloan, Ashish Arora, who I think is at Duke. They've all published interesting things. Actually, just before the call, I was reading a paper called "Are Ideas Getting Harder to Find?" By Nicholas Bloom, Charles Jones, John Van Reenen, and Michael Webb. So people, there's work in this stuff. I think there should be more work. It should receive more attention, and more of it should actually get applied in practice.
Okay, so now I see that we're out of written questions. Anybody want to speak up and ask a question? Just unmute and talk. We'll take a few of those, see how it goes.
Yeah, hi. So this is related to the second AGI question from earlier, but there's been, I think this is Nick Bostrom's idea, this proposal that as technology accelerates, it gets ever more dangerous because, the classical example is teenagers synthesizing horse box in a garage and so on. So since you are suggesting that invention is, that progress is closely tied to this experimentation, and as you were saying earlier, you don't really know what you get, that does suggest that it becomes incredibly hard to contain technology. So I was wondering whether there are historical examples of something like that happening. something, you know, like akin to someone inventing the nuclear bomb and like keeping it secret, or like being up to no good.
Well, if there was an example of somebody keeping a powerful technology secret, I guess we wouldn't know about it. If they did a really good job, right? I guess maybe they kept it secret for a long time. I don't know of examples of keeping things secret. So there's at least two different types of technology risk, right? There's the risk of accidents, and then there's the risk of malicious misuse. I don't know a lot about what to do about malicious misuse. That seems like fundamentally a moral and political problem, and it's something I've spent a little bit less time thinking about, although it's very important. In terms of accidents, I think that, okay, technology is risky. So progress is risky in general. Technology is power, and power can be used for good or evil. It can be used wisely or foolishly. It can, and it can get out of hand. But not all technology increases risk. I think maybe technology by default increases risk, or if you're not paying attention to the risk, level over here while you're experimenting over here, maybe the default is for the risk level to go up. But when we set our attention and deliberately set as a goal to create safety, to reduce risk, we can often do that through safety creating technology. So not all technology increases risk, even if technology increases risk by default. Safety technology decreases risk. And so I think the key question, if we're worried about technology risks in this context, especially in the context of accidents, is how do we make sure that we create safety technologies at an appropriate pace and in an appropriate balance with the risk-creating technologies that we are pursuing? So if we just blindly pursue more power, more speed, more whatever, and we're not paying attention to the potential risks, then I think we're in a potentially dangerous situation where things are sort of running ahead, and we're just kind of like not, we're asleep at the wheel, or whatever you want to call it. But I think if we pay attention to that and we recognize that, as new technologies come along, we need to think about what kind of risk they might create, and then put an appropriate amount of resources appropriately early enough into creating safety mechanisms to counter the potential risks. Then I think we can continue to move forward with technology and continue to reduce overall risk, for the world, as we've been doing over the last couple hundred years. I think that one thing, so if you look at the history of technology, I think that we have historically not been very good at anticipating risks. Generally, the things that, it's not that we don't worry about new technology, it's just the things that we worry about are not always very well correlated with the things that turn out to be real problems. And so and even when we do anticipate problems, or when we could have easily anticipated them, we're not necessarily good at doing something about it ahead of time. One example is antibiotic resistance. Alexander Fleming, in the very early, the microbiologist who discovered the action of the penicillium mold that led to penicillin, the drug. Fleming, early in the antibiotic era, foresaw the potential of antibiotic resistance just on general evolutionary principles. It did not stop doctors from way overprescribing antibiotics in the early days. So we need to get better at anticipating problems. We also need to get better at heeding the warnings. I think there is some evidence that we are starting to do that and that we can do that. And especially within, so I mean, the movement towards AI safety is a case in point. Another similar phenomenon is the attention being paid to gene safety. So multiple times in history of genetic engineering, people have sort of called for a bit of a halt, even a moratorium on experiments, and called for a conference to get together and talk about safety procedures. And they were able to, through focused effort, anticipate what some of the risks might be, think about what different types of activities had different levels of risk, and come up with kind of appropriate practices, protocols, and techniques to contain risk. And I think we can and should do, probably should do more of that with more technologies going forward.
Okay, great. We have another question in the text chat. Sriraman asks, how much role do you think narratives in the form of science fiction play in progress?
I think narratives are very important. I think they give people a vision for the future. I think they help communicate ideas of the very idea of progress, the idea that we can make the future better, that improvements are possible and desirable. They inspire people in particular, to go pursue particular types of innovations, and they inspire people to, just pursue innovation in general. I mean, man, how many geeks got into science and technology through Star Trek? Like an enormous number, and many of them, some of them specifically went into space technology and into aerospace because of they wanted to make Star Trek real. So I think they're very important. And one of the things that bothers me is how much it seems that in recent decades, sci-fi has taken a turn towards the dystopian, and that people have gotten kind of more pessimistic, more negative, and that we don't have as many positive visions of the future as we used to.
Okay, Sriraman also asks, do you see any trends in the incentives for technology and engineering to exceed science's grasp?
Trends in those incentives. I haven't thought about that. That's a great question. So I don't know. But to the extent that everything gets more accelerated, and today, if you come up with any product, you have almost instantly a global market for it, because you can market to the whole planet through the internet, and you can distribute anywhere through an extremely efficient, cargo distribution network, supply chain. Seems to me like the incentives would be, if anything, larger than they ever have been. The counter on that, by the way, is how much of a headwind you're going to face in terms of regulation. So I think a lot of areas are now highly regulated in a way that they weren't before, and that adds costs and overhead.
Josh Sachs asks, do you think Enlightenment values are important for progress, or is it a coincidence in timing?
Huge question, but fundamental answer, yes. I do think that the philosophy of Enlightenment is kind of a major primary cause. This isn't necessarily something I feel I can prove yet, but it's something I do believe. Steven Pinker's book Enlightenment Now makes a good case for this. Even better, I would say, is Joel Mokir's work. I mentioned him before as an economic historian, maybe my favorite economic historian. Actually, a book of his that got me into this whole studying progress thing is called A Culture of Growth, in which he basically says that he basically shows how the Enlightenment laid the foundation for the Industrial Revolution. And he gives a lot of credit to Bacon and Newton. It's probably because of that book that Bacon showed up on slide 2 or 3 today. And he says that essentially the very idea of progress, the idea that progress is possible and desirable, is a modern concept that originated in the West in the 15 and 1600s. And that before that, and in most places and times, people didn't even the idea of progress. They saw history as relatively cyclical. And in fact, they often had the opposite idea. The opposite to the idea of progress is the idea, Mokir says, of ancestor worship. The idea that our ancient ancestors were the greatest people who ever lived, that their accomplishments far surpassed anything we will ever do, and that their all knowledge that matters was revealed to them in ancient times, and that really all we can do is kind of pay them appropriate respect, learn from their ancient texts, and maybe produce a little bit of commentary on them where we can wring deeper and deeper levels of meaning out of them through more and more exegesis on the classic texts. That's kind of where society was for a while. And so he tells in that book about how we broke out of that and came to the modern concept of progress, modern in a broad sense, and realizing that we could actually surpass the ancients and, take the world to a better place than it had ever been. And the core ideas of the Enlightenment, which Pinker sort of identifies them as reason, science, and humanism, I do think are important for all of that. I do sort of believe in that fundamental power of the idea of reason as an overriding principle in life and guide to life. But all of this stuff, of course, is deeply and hotly debated. But
okay, well, thank you, Jason. This is a chance for everybody to unmute and applaud. So thank you for the lecture and for the Q&A.